Hi, my name is Jai Pathak and I am a software engineer at Razorpay. As a member of the platform team, my focus is on building and maintaining highly available and scalable systems that power our payments platform. In today's talk, I will be discussing the topic of Edge at Razorpay, the API gateway for DDoS protected high scale environments. As we all know, API gateways plays a crucial role in modern software architecture, serving as a central point of entry for incoming traffic from various sources. However, building and maintaining a highly available API gateway at scale is no small feat and requires a deep understanding of the underlying technology and architecture. So, without further ado, let's dive into the topic of and explore how we designed our systems to tackle DDoS at high scale, ensuring quality of services. About Razorpay. Razorpay is a leading fintech company in India, offering digital payment solutions to businesses of all sizes. Our mission is to make payments simpler and more accessible for everyone. We offer a wide range of payment solutions, including full stack payment and banking solution. We accept, process, and disburse payments, thus ensuring our presence with every aspect of money movement. We also provide neo banking service, which provides businesses with a range of financial management tools to manage their finances effectively. We have Razorpay Capital, which is a lending platform that offers working capital loans and other products to businesses using their transaction data for underwriting. Razorpay focuses on a variety of merchants, ensuring seamless integration. Our payment solutions are very easy to integrate, and we have detailed documentation, SDKs, and plugins, which helps developers to get started real quickly. We are proud to serve over 5 million businesses across India, ranging from small startups to large enterprises. Our customer includes some of the leading names in e commerce, tech giants, food delivery, travel, education, and more. Let's start with a quick introduction to the Razorpay way of handling requests, which covers the request lifecycle and every component associated with it. In terms of using Razorpay, there are two main entities associated with. Merchant. A merchant can be a business or individual who uses Razorpay to receive payments, and there are customers who initiate transactions by making payments through Razorpay Payment Gateway. All of the requests made by the sector using the suites of products which are being provided by Razorpay are being served via the API gateway at Razorpay, that is Edge. Edge provides functionalities used across requests such as authentication, authorization. Edge is in a privileged position to generate rich insights about the API requests and also provide perimeter security. Post processing, Edge forwards requests to the downstream services. To understand more on the infrastructure, let's see how a request gets processed at Razorpay. Razorpay leverages blue-green deployment strategy, where we use Route 53 to distribute the traffic to these clusters. Both of the clusters are mirror of each other. Now, when the request hits either the blue or green deployment, it is routed through an AWS load balancer, which helps to distribute the incoming traffic across multiple instances. This also improves availability and helps to prevent overload on any of the instances. After the load balancer, the request is sent to Edge, which is our API gateway. For today's presentation, we'll be talking more about the capabilities of Edge and emphasize more on how it helps in generating insights and provide a scalable and reactive DDoS preventive mechanism to secure the Razorpay infrastructure. Edge uses several technologies to provide its functionality. Razorpay is completely on Kubernetes, where we leverage AWS managed EKS services. Every single container is Dockerized. We use AWS Aurora to store Edge configuration. For our rate limiting counter data store, we use AWS Elasticache Redis. Our custom logics are built using Lua. We also use Kong to extend the web server functionalities. Edge uses Golang to implement some of its core functionality as well as custom logics. In summary, Edge uses a powerful combination of AWS services, databases, scripting languages, web platform, and containerization technologies to provide a highly scalable and performant API gateway. To talk about some more of the capabilities at Edge, Edge supports a wide variety of authentication mechanisms along with RBAC capabilities and fine-grained authorization policies. Edge also provides powerful monitoring capabilities. Stakeholders can set up alerts and notifications based on various metrics such as API usage, error rates, latency, and much more. Security is a top priority for Edge. The platform provides a range of security features such as IP whitelisting and also helps in analyzing malicious requests. Another important capability of Edge is capturing insights, which contains detailed information about every request. For example, request pattern, IP reputation score, user agents, and what are the security measures being applied on any request, etc. Edge also provides DDoS protection to its customers. By leveraging rate limiting, Edge is able to detect and prevent DDoS attacks before they impact any sort of API availability. Edge serves 600 million average requests on a daily basis. During a burst scenarios, this number may reach up to 3 times. Edge handles 5 plus billion peak requests during any day. Working at this scale, it was important for us and for Edge to ensure protection against DDoS. Bad actors conduct distributed denial of service attacks using advanced mechanisms. Razorpay enables merchants and individual customers to leverage our APIs for accepting and making payments. Given the complex nature of payments, it was a challenge for us to protect against DDoS mechanism or attacks using an out-of-the-box solution because we had to distinguish between small merchants and large enterprises. So we had to build something custom to suit our needs. One of the measures to prevent DDoS was to make the rate limiter intelligent enough to support this traffic and proactively ensuring a safeguard against attacks. Let's look at the journey of rate limiter evaluation and consideration which we have gone through. This particular slide represents a traditional setup for rate limiting with Redis as the data store. Incoming requests are being checked against Redis based rate limiter counters. A simple setup. But why this setup was not feasible for us? Despite being scalable and highly available, Redis has its own set of limitations, and this traditional setup also had its own set of limitations. At Razorpay, we provide a variety of custom attributes to set up rate limits on. Due to this, for a single request, multiple Redis calls were being made. Redis network calls can become a network overhead for rate limiting service if there are too many network round trips. Every single network call can also help or lead to an addition of latency by a couple of milliseconds. Every decision was being made at Redis. So for our use case, this can result into multiple Redis call for every request, thus resulting in a significant delay in the evaluation of request. To overcome this limitation, we worked on top of the traditional rate limiting setup where we used an internal shared memory cache to keep a copy of counters and state. This setup enables faster throttling decisions by rejecting early, which in turn reduce the number of requests sent to Redis. If the incoming request falls within the allowed rate limit, the plugin updates the shared memory and updates the countersink to Redis and thus forwards the request to the upstream service. However, in the case if the incoming request exceeds the rate limit, the plugin checks the shared memory and if the request has already been throttled recently, it returns an error response without syncing it to Redis. This setup also helps in faster decision making since the final decision to throttle the request is decided by the shared memory cache. The modification provides an efficient and scalable solution to handle high traffic rate limiting scenarios. However, there were still some limitations to this particular modification. This modification becomes a bottleneck with requests which are legit, since Redis calls are still needed in order to maintain sync. To overcome this challenge, we work further on optimizing our Redis calls. In addition to the previous approach of rate limiting with an internal shared memory cache, where multiple Redis sync calls were required for a single request that had multiple rate limit rule setup, we decided to work further to group Redis calls into batches to optimize performance. Instead of sending multiple sync Redis calls for every request, we now group them into a single batch call. The rate limiter plugin fetches all the rate limiter counters for a request and sends them in a batch to Redis, thus reducing the number of network round trips. By grouping Redis calls into batches, we can minimize the network overhead and improve the performance of the rate limiter plugin, especially in high traffic scenarios. The batch approach also helps preventing Redis from being overloaded with multiple requests from the rate limiter plugin, thus ensuring optimal performance and scalability. With this approach, we are able to optimize the number of Redis calls by more than 60%, and also we are able to improve the plugin latency by more than 40% by reducing the network overhead. However, we still needed to make one Redis call per request. Operating at Razorpay scale and the numbers that I have described before, where we cater millions of requests every day, this was still a performance bottleneck for us. So, on top of the previous approach, where we used batch Redis calls for handling multiple rate limit rules for a single request, this optimization further improves the performance by using an adaptive sampling strategy. The strategy decides whether to make Redis calls for a particular request or not. So, what is adaptive sampling strategy? The adaptive sampling strategy is a custom built solution for our use case which uses an algorithm to decide when to make Redis call for a given rate limit. This approach reduces the number of Redis call and optimizes the use of resources. Razorpay uses complex logic with various dynamic parameters, a simpler equation of which is highlighted over here. The algorithm uses a set of variables including available tokens and a sampling constant to count the rate limit for each incoming request. It also considers the dynamic pot count parameter to decide the number of requests. By analyzing this parameter, the adaptive sampling strategy decides whether to sync the data with Redis or not. This strategy improves the performance of the rate limiter by reducing the number of Redis calls drastically without deviating from the actual configuration. It also helps to optimize the use of resources and prevent any sort of overloading at Redis or inducing any network latency with unnecessary calls. I'll give a quick example where we display the use of the adaptive strategy. Consider an example where the rate limit bucket is configured for a particular rule. The max tokens has been set to 100. We have set the refill rate as 20 per minute. The sampling constant has been set to zero point 0.5. So when the bucket is refilled, the number of request post which a Redis sync call has to be made is calculated as 10. So instead of making 10 Redis sync calls, we are going to wait for 10 request post which we will make a Redis call. After the 10th request, we'll again calculate this constant and we'll derive the next number on which we have to make a Redis call, which will be reduced to a further less number. As we go more granular on the number of requests, we are moving closer from eventual to strict consistency. So with this adaptive sampling strategy, we were further able to reduce the network calls by further 80% without inching accuracy. Another limitation with having a single rate limiter plugin is to opt in request related data for rate limiting rules to decide on throttling. Let's take an example of JWT token. Edge needs to perform signature verification in order to derive consumer identity. This is a really heavy CPU intensive process. Therefore, to avoid load in case of malicious traffic, having a rate limiter post evaluation of auth will have impact on performance as well as overutilization of resources. To solve this, we segregated our rate limiter plugin into two sections, contextual and non-contextual. Contextual data have a dependency on the outcome from any derived value which is not present in the request, whereas non-contextual data relies on the data which is already present in the request. The non-contextual rate limiter plugin evaluates rate limits on the basis of the available request data and throttles requests much faster before performing any sort of additional operation or computation at the API gateway. This optimization helped us to reduce the overhead on other operations, resulting in much faster and more efficient rate limiting. This approach also helped to ensure that the rate limiting plugin can handle a large number of requests without putting any sort of pressure on our API gateway, thus improving the performance and scalability. With all the optimization and enhancements, it was still important for us to ensure the protection of API gateway from abuse traffic. Thus, we decided to use AWS WAP to ensure API gateway is protected from abuse traffic and also to reduce the possibility of any impact on availability. As I have mentioned before, Edge sits in a privileged position which helps us in generating rich insights for every request that is being made. We use this same insight to build intelligence which can not only help in detecting and preventing but also helps us in mitigating any sort of DDoS attacks. The events, or as we say them as insights, are fed into machine learning models in real time which are built in house. This model generates multiple insights which falls under major two categories. One is to identify any sort of malicious pattern or abuse traffic which is near real time. So any similar pattern observed via this machine learning model will result into addition of a WOF rule to block such traffic. Second is to derive rate limits based on historical pattern. Apart from real time, we use the data and insights which are being provided from Edge on the basis of the historical pattern and on the basis of the usage and the periodical analysis. Rate limits are being derived which can be based on any sort of request data such as IP, user agent, consumer, etc., or a combination of this parameter. The usage of these historical patterns helps us in creating rate limits for any sort of scenarios which can result into a DDoS. Apart from using API gateway to throttle requests, we also leveraged AWS WAP using the machine learning model as you can see in the particular diagram. The API gateway generates insights which are being fed to a machine learning model using a data store. This machine learning model further computes and identifies any sort of patterns which can cause any sort of abuse traffic in real time. The WAF rules are being set and helps us on top of the rate limiting rules which are being available at the API gateway. So we use a powerful combination of AWS as well as our own customization of the rate limiter plugin to ensure detection as well as prevention against any sort of DDoS attacks. I would like to quickly summarize about our enhancements over the traditional rate limiting. We use internal shared memory cache on top of Redis to throttle fast. We have done grouping of rate limits within a single Redis call, optimizing further the number of Redis calls. We also ensured the correctness of execution using the adaptive strategy mechanisms in order to further optimize the Redis calls. We segregated the rate limiter plugins and evaluation of rate limiter plugins on the basis of context. We further introduced machine learning models to derive insights that are being generated from Edge in order to set up automated rate limits using the historical patterns. Now we have a setup which provides automated response to any sort of DDoS, thus helps us in prevention and mitigation using the AWS WAF. With this, I would like to conclude my presentation. Please reach out to us if you have any questions and suggestions around the topic. Thank you for joining me today, and I hope you find this talk informative and useful.